and we really grateful to Robert being able to give this talk for us here in SBMF. I told him that he already, I don't know if there is this word in SBMF, but if there is, there isn't, we're going to create a award for best title, and you're going to give to you.
Yeah, hopefully the title is not the best part of the presentation.
Yeah, very exciting. Yeah, everybody looking forward to your talk, and really great to have Robert here and talk about Open MBE, and just give a brief introduction about Robert. He's the technical group lead of the Software and System Solutions Engineering Group and the lead for the Computer-Aided Engineering System Environment at NASA JPL, Jet Propulsion Laboratory. His team provides an environment for engineering modeling, supporting systems engineering and analysis activities, leveraging and integrating with software environment. So Robert is internationally recognized as an industry leader in MBSE, model-based system engineering, and model-based engineering as well, using his leadership role in the Open MBE community and as a NASA representative at the OMG for SysML to align the different model-based aspects. So prior to that, he developed a control and instrumentation system and software for large telescopes at the European Southern Observatory, pioneering MBSE for large systems, applying model-driven technology, and for particle accelerators at the European Organization for Nuclear Research. So it's a really interesting talk, really, everybody looking forward to it. So thanks a lot. And without further ado, yeah, the floor is yours.
Okay, I'm presenting from a hotel room, and of course they decided to start hammering and drilling right now. So if you hear some noise, I hope the noise canceling of the iPad works fine. But if you hear some noise, it's not that because there's other people in my room snoring. It's like because they are hammering and drilling. Anyway, so many years ago when I still worked on telescopes, I was traveling a lot of times between Munich, where the headquarters of the European Southern Observatory were, and the observatory in Chile in the Atacama Desert at Cerro Paranal. And there was a lot of stress getting that telescope to work, and I was responsible for the telescope control system back then. And since it was an international organization, there were occasionally high-profile people visiting to see how their people's tax money is being used. So at one occasion, the Prince of Spain and his delegation had announced themselves, and I was the chosen one to kind of demonstrate how, in that very kind of unstable phase, because a lot of things were working, or they were working one day and not the other day, kind of demonstrate how this 400-ton telescope moves around with micrometer accuracy at high speed. And it was scheduled for like after lunch. So I went there in the morning, tested everything. I went through my script, worked, right? And then worked on something else. And went for lunch, ate hastily my lunch, went back up to the mountaintop just to verify again. And guess what? Didn't work. So when I initialized the axis, it just slammed down 30 degrees, this huge thing, the emergency brakes engaged, panic. And so checking what might have happened and so on. So in the end, it turned out that after I checked everything in the morning, I changed something else somewhere else, which was supposedly unrelated, but apparently was not. So I could roll back. The prince in this delegation came. I moved around the telescope. They were happy, left, and I needed a nap after that. But today's talk is about kind of having that as a background, right? We are producing a lot of more and more complex systems with a lot of dependencies which are implicit. And what we lack often is some systematic approach how to qualify and validate that system. And the title, yeah, for the ones who know math a little bit, it's the kind of riddle that you can try to solve throughout the presentation, why it's about monsters and dragons. But for the ones who find out, they'll get a piece of chocolate when I meet them in person. Okay, let's get started here. So what are we doing so what is JPL? So JPL is a federally funded research center. So it's directed by NASA, but the funding and the oversight comes from Caltech. So it's kind of in this in-between situation. And what do? We fly to other planets and land on them even, right? So we heard about probably the Mars program and the current rover that is roaming on Mars, Perseverance, fly to Jupiter and Saturn, but also have interstellar missions like Voyager, but also Earth observation missions. So in this context of the presentation, which is mainly around the theme of system engineering, what do we consider what a system engineer needs to do? What's a system engineer's task? So the system engineer needs to guide the concurrent collaborative design of very complex technical systems, right? To have like a one-sentence description. So that requires leadership, right? Have to there's always a huge team involved, particularly with these huge programs. It is always around some cyber-physical systems where we have to architect, design, develop, validate and verify, and then also operate. And we have to manage, a system engineer has to manage all that complexity, right? Which is across disciplines, and this in complexity is increasing, or has been increasing. What you see on this slide is the project team of the current Mars mission of Perseverance. So there's a lot of people that work on one project, and they often communicate still. You might be surprisingly for you, in particular the formal methods people, spreadsheets are very popular, you know, throughout everywhere, and they communicate through those spreadsheets, right? To eventually do this, right? To land on another planet. So, or even fly, right? Let me see. There's some lag in the. Okay, here we go. Flying on Mars, something new, and it even works. But it takes a lot to get there, right? So how can we get from an Excel sheet, I'm a little bit exaggerating, to that, right? So how do we bridge this gap from kind of something very informal to like operating and developing a very complex system? So it takes people, a lot of people. It takes requirements, spreadsheets, documents, processes, workflows, and a lot of testing, right? And often those, come on. So often the project starts simple, right? You have some models, some spreadsheets, PowerPoint presentations, documents, and as you go through the development process, the engineers iterate on their models, on their data, on their analysis, right? And this kind of network proliferates, right? So you have more and more documents, more spreadsheets, more models, right? And at some point you have kind of this maze of data which is distributed, right? So it gets complicated very quickly. And what we observed is that there's a bad ratio of the real engineering that people do versus the overhead, right? So they have to repetitively entry data, right, in spreadsheets or another spreadsheet, and there's different people entering data. There is this version confusion, right? What is among all the spreadsheets, documents, PowerPoint, what is the right version? And the constant search for the right information, right? So what is the current version? What is the right version? And where is that piece of information that I need to take my design decision? So how do we connect all those things together, right? So that's the big question that we are trying to work, and the vision that I'm going to present in this talk. And this is where the dragons and the monsters come in. First, the monsters come in. So what we see is that with this ever-growing complexity of spacecraft, and you have more functions, you have more hardware, you have more software. And why is there so much software nowadays, right? Makes everything so complicated. And these monsters occur and reproduce, right? The observation that we have is, or that we make, is that those silos, which we call the monsters, they occur, right? So we have these different parts of the system, like the flight software, the ground data system, remote engineering unit, right? Those things are developed by different teams based on some common requirements, and there's a lot of connections between them, but most of them, or many of them, are implicit, right? So it's really hard to understand what those relationships are between those silos, right? For example, which is very simple, how do we check requirements against the tests that we have to do, right? Or how do we perform an impact analysis across the board if something changes, like some engineering change request that trickles down from requirements to the test through our architecture and design. And our claim is that we can resolve those monsters by using models to capture those relationships, right? So turn those monsters into a solution. So those monsters, no, they're not simple monsters. They live in a discontinuous space. And so there's an overhead if you try to connect all those things manually and provide and to break these silos up, right? It's really a big problem. You have all these disconnected areas with implicit relationships, in particular using Excel, and this fractured, non-holistic environment, right? And the qualification process, right, to qualify a system from the very beginning, from the early concept design to the final product, does not work systematically, right? That's the huge challenge. So the concept we have been kind of contemplating is digital twin pipelines that evolve with the system development, right? So we are thinking of the system development in this case as a spiral, right, that you see here on let me see if that thing works. Okay, so here's the spiral that you see, and you have, like, along this spiral, you have certain deliverables, right? Deliverables of the system at different phases of the life cycle. And corresponding to that, you have this, what is represented here as a fractal, right? So you'll see this fractal that kind of gets more and more detailed as you progress through that system development life cycle, right? On those, and each leg of each fractal represents a part of a digital twin pipeline. So this is the concept that we are trying to implement, right? And there's a red thread going through those. So those are not disconnected pipelines, right? So they have, from in the very beginning of the system development, might be very simple, right? That's why we have only like this simple fractal. But as you go along, you add more and more detail, more and more fidelity, and you get more and more clarity of actually what you want to build until you can build it. So the correspondence between the spiral, the digital twins that are represented here as the fractals that get more and more detail, and the continuity between those fractal pipelines. That's somehow the analogy we envisage. So what we want to follow is an evolutionary pattern to keep all those things connected, right? So these pipelines we want to expand and evolve them as a digital twin, right? We want to manage change packages. So we want to have like the ability to say, okay, we make a change, right? And it trickles down through all those artifacts that we produce throughout these pipelines, because the products are produced by those pipelines, which might be a model, which might be a document, whatever it is, piece of code, right? We'll see that in a bit. If we change something somewhere, right, might be a requirement, and it trickles down to the test, till the test, right? We want to say, okay, whatever has changed in all this pipeline, we want to kind of tag as a change package. So we know requirement changed, design changed, code changed, test changed, and so on, right? These are the things that change. That's what we think of a change package. And the fractal approach is that each of these qualification steps, so every time we kind of move from one fractal pipeline to the next one, there is some kind of criteria that we have to satisfy that qualifies the products that come out of that pipeline, but they remain valid over the time and get elaborated, right? So we have, for example, early on simulations in a model, but they are still valid for the software that we actually produce later on, right? Along this spiral build of the system representation. So what we want to do is to kind of make this process that connects systematically that information, a commodity, right? So the big challenge is always how accessible are those things to like the average engineer, right? I mean, there's all kinds of nice things that you can do. Model checking is actually one of them, right? It has been for a long time very inaccessible. There's like you need the expert that can do it, but for the average engineer, it's really difficult to access. But there's many things like that, right? So the commodities, there's something like we want to make a commodity that it's kind of transparent, kind of transparently integrated in the system development process and accessible to the average engineer, right? So you don't have to have this special knowledge. You make your engineering model, you run it through some pipeline, like a model checking pipeline, you get some results and you can iterate on that without having this expert knowledge. And those, so we're kind of projecting this spiral into these fractal pipelines, as I mentioned before, increasing the detail and the fidelity. Right? And with each twin that correspond to the increments in the spiral, we have a degree of qualification comprehensiveness, right? So there's this qualification step every time we add more detail. And they build on top of each other. And this is what we call the dragon architecture. And so the dragon architecture, or the claim of the dragon architecture, is to have like this formal qualification of system modeling and software, right? You see often that like now that software is more and more permeating any kind of system, right? You have software-defined everything, software-defined, start with the software-defined phone, software-defined vehicle, and there will be hopefully at some point a software-defined spacecraft, right? So there is not really kind of this, there should not be this separation, maybe organization there could be, but like process-wise, the systems engineering part, the software engineering part, they have to be integrated, right? And because they are dependent so much on each other. Right? So what we want to have is, produce is a repeatable, executable representation of the system and all the relationships at those different levels of fidelity, right? As you go along that system development process. What we also want to have is an explicit qualification record, right? So there's always audits where people come in and where we have to demonstrate, okay, there were changes, this is what we develop, but can we trust that thing that we produced, right? So if it's all ad hoc, email chains and Excel, it's hard to show that qualification record. Our belief is that if we pursue the systematic qualification with these digital pipelines, we actually get kind of out of the box that qualification record, right? With the change package management and the pipelines that produce the artifacts, we have that trace throughout the life cycle of the system development. And that gives us this systematic process to develop the system. And this is a kind of the say what we envisage as the Dragon architecture, right? And at the top, you see a number of applications and services that we currently use in our system environment. But what you should kind of see there, and the Syndea, for example, mentioned, which is one application that we use. But what the top part kind of represents is that there is this global traceability, right? We use all those applications and services for different purposes, and they produce some artifacts or help producing some artifacts, but we need this global traceability across all those applications and services and the products they produce. Right? And in kind of the middle, you have this kind of functional flow, let's say, right? There's many other things that could be. It's more representative, right? It's like a conceptual level. The idea is that we don't impose any kind of process, but this is some kind of like conceptual functional flow through a system development. So we would have some requirements, right? Some design documents. We would have some executable system model that with behavioral elements and scenarios that we use to author the design documents. And those models, they would be fed into different things. For example, into model checker that would produce model checking results. But we want to have this traceability, right? So you would see something like using something like test rail, would kind of keep track of those model checking results. And we want to know, okay, these model checking results, they correspond to that version of the model checker, to that version of the model, right? And as that model increases in fidelity, we want to be able to trace them, right? And the executability is the same thing, right? We'll have an executable model that we can simulate, analyze, produce test results or traces. And that would also kind of be another pipeline. So this is kind of the pipeline, right? This is the from requirements to the artifact repository. That's the pipeline, right? So there should be at any time of the system development life cycle, there should be a piece of everything there, right? At different level of fidelity and detail. Right? We would use the same model to kind of generate code, not only source code, but also test code that would then be built, test, analyzed, but also be used to generate documentation, which again would be then reviewed, end up in software documentation, and eventually end up in a formal change package, right? So the change package mechanism that I mentioned before, you could imagine can come in at any level. One typical scenario is the requirement changes, and then it would trickle down through that flow, right? And every change along that pipeline would be part of that formal change package. And then on the lower part, we have this kind of DevOps continuous integration model, right? So we want to have automated as much as possible. So for modern system engineering, the big paradigm shift is somehow moving from like a document-centric, where you write all these things in natural language, to kind of like formal language and automation, right? So what we need is to make this shift for the average engineer easy, right? This is where the commodity comes in, right? How can we enable them to use formal languages and to have an increased degree of automation, right? Because you cannot do that manually, right? Well, you can, but only with heroic measures, right? So we need as much automation as possible in this to support this kind of architecture, traceability, change package management, and so on. So we have started some prototyping activity and also some production activity of parts of this Dragon architecture, which I will walk through right now. So the very first one was related to the remote engineering unit, which is some critical component in the spacecraft that includes the mission clock, fault protection processor, and so on. And there, the team that was working on that came to us asking, so they had the requirements and they had to perform some tests, and they kept track of the let's say the verification of the requirements in some Excel sheet, right? So they would have the requirements in some database, they would perform the tests, and then they would keep track in some manual way of that, right? Which is hard to do, and it comes back to like this, okay, how do we get actually from the Excel sheet as the kind of representative to a flying to a helicopter on Mars? And in this case, it was surprisingly simple, right? And we established a pipeline as part of this Dragon architecture, which enables them, okay, we capture the requirements already in some database, they're already there. We add another thing, that pipeline, where they can keep track of either manually in this test management system, right? Or when there is automated tests, that those tests would be automatically published programmatically to that test management system. So we can have kind of this history of when did we test which version of the software and what results did produce, how many failed, how many partially succeeded, how many were not performed, right? And to move these kind of test logs also that were produced onto the web, right? So that they're accessible and not on some local machine. But also to enable this traceability which is based on business process, right? You have to demonstrate that you perform the test to verify some requirement. So we helped in this case using a application service which is Syndea, to establish that traceability between the test artifact, a test result, and the corresponding requirement. But everything would be like in an accessible, queryable database, right? So what we can do is then, once that traceability is established, we can query it, we can run reports on it. So we have this auditable trail, and we have our qualification record, right? That is programmatically accessible, right? So this is this one part of a pipeline, which is rather simple, but in the end, very effective. We built a few other pipeline prototypes that have evolved meanwhile more. So one is the pipeline of model execution, code generation, and test, right? So people have been building some models for flight software. This is this FSW here, but they were not executable. They generated some code from it with some technology, homegrown technology. So what we helped is to kind of update those models, and actually it turned out there was not much to do to make them executable. So we would be able to perform simulation before actually code would be generated, to check the logic, for example, of that specified behavior, to have scenarios specified that were used in the simulation to test that logic, and later on also to test the software, and also to trace the requirements to the resulting tests, right? So you have again with Syndea would trace requirements and to the system model and the scenarios that were produced and used to test the model and the generated code, and then you would generate the source code, not only the source code but also test sequences, So here is a little example. So you see on the left, you see a SysML model with some structure. It has some state machines to specify the component behavior, but it also has sequence diagrams, right? So that would drive that simulation and the execution in that part of the pipeline, right? So that allows us this early validation of the logic. But then we will use that to produce the application code on one side and the sequence diagram. So from the state machines specifically, right? Transform that and produce the application code, but then also use the sequence diagrams to produce the test code, right? So then we have again this kind of pipeline. We would use the same thing early on, right? We would build maybe a very early simple model, right? That increases with fidelity over time. We would have our test sequence that validates that model, but then produce another artifact that we can trace to, and the same test code, run that test code that comes from that sequence diagram in the model, run against the application code, right? And it should ideally produce similar or the same results. So that's one example of this kind of pipeline of model execution simulation, code generation. In this case, we use the Komodo platform from OpenMB, and we'll hear about OpenMB later on, and then the code. Another example is document generation. So the flight software developer, they have the requirement to demonstrate that their code satisfies a certain requirement. So they have to kind of keep track of, okay, this piece of the code implements this kind of requirement. So they have to demonstrate this traceability. So the prototype we built was that the flight software developer would kind of provide with a specific markup as a part of the comment of the application code, a hyperlink to the requirement, right? And that has to be a manual process, at least partially. But we would detect when we produce the documentation using Doxygen, we will detect that hyperlink and automatically produce and generate and create that relationship is using Syndeia again to have this traceability between that piece of code and that requirement, right? So it's not only that hyperlink, but we would have this traceability connection in that Syndeia database that allows again to query it, run reports, and so on, right? So it would be this relationship between the code file in Git and the requirement in Doors, for example, right? And display those end points of the relationship also in the documentation that we produce from the source code, right? And you can think of that further, right? We could do it, probably generate that automatically, because we might have already that connection in this. If it's model based, right, we can have that in the model, have there that relationship and propagate that for the generated code automatically, right? So we would have the relationship from the model to the requirement, but then also from the code to the requirement and to the model, right? So here is the little example. So you see, okay, there's the code, and there's some comment and some documentation. And then there is this markup with the hyperlink to, in this case, it's a JAMA requirement. And when we generate the documentation, okay, the documentation includes a table that points to that requirement. So we have in the source code documentation also the traceability to that requirement included. But behind the scenes, we will also generate that connection using Syndeia that we actually can query. So what are the technologies that we have been using to enable parts of this Dragon architecture? So one thing is, one part is, and that's like a fundamental part, is the open MBE, the open model-based engineering environment. You'll hear later more in the tutorial that will be given, but just briefly, the kind of concept in open MBE is to close this gap between engineering model and documentation, right? I mean, 20 years ago, everyone was running around, model-based system engineering, the documents will disappear, we will be free, we'll have only models, right? And we were all wrong. Documents exist still, and they will always exist, right? The kind of change that has happened is that we have to integrate, right? We have to close this gap, because usually people, there's always some kind of model, right? And people copy paste information into a document, in the Word document, for example, and then they ship it. But as soon as you do this copy paste, you have this disconnect immediately, right? You lose the traceability. So the Open MBE infrastructure allows you, and this is kind of conceptually symbolized with this graph. You have some models and some information in these different models, but you want to embed in a document, as we call it, as a transclusion, this piece of information. So there is kind of a live connection, right? So that we embed this information in engineering model and therefore integrate that model and documentation part, right? And has to be version controlled, CM'd, and all the usual stuff. So out of this need to bridge this gap, the OpenMBE community has formed and has been in existence for like, I think 7-8 years now. And it's a community for open source modeling software and models. So people, organizations, open source contribute software, right? And there's parts of the software that for OpenMBE that you will hear about in the tutorial. The people contribute models. Sorry? Someone's mic is open. And of course, it's used as a forum to exchange these ideas, right? All these organizations, and meanwhile we have, that's an old number. Meanwhile, we have more than 400 or 500 members from different organizations, and we have regular community meetings, leadership meetings, to bring forward the cause for a model-based engineering. So you're invited to join the community. Part of this vision is to build this kind of having like this linked data documents or linked data across that architecture. They have this global engineering ecosystem vision, right, around Jupyter. So Jupyter is kind of a pillar in this architecture, right? So because it has this multi-language analysis capability. It comes originally from, as most of you probably know, from more from the data science side, but we have used it more for engineering, actually, and engineering analysis, right? Integrating models, integrating those pipelines, right? We would query things in one repository, process it, publish it to another repository, automate that process by executing that notebook, Jupyter notebook, for example, periodically, right? And kind of enable this data-driven analysis as a service, right? This is again the commoditization approach that make it accessible to people. And standards play a huge role there, right? So in particular, the upcoming and emerging SysML v2 and API services standard, right? And if you kind of think of the web as we see it today, right? I worked at CERN in the late 80s, early 90s when I was there when the first web server went online. And OpenMBE is somehow similar, but for engineering, right? We want to enable this global engineering ecosystem. For the ones who don't know, haven't heard about Jupyter, we want to have it like as a hub for analysis and visualization for models, right? This interactive exploratory browser-based computing environment that can be used for almost anything we discover. There's not really a limit, right? So that's a major piece. SysMLv2 is also a major technology, and I'm currently now at the OMG Object Management Group meeting, participating in the SysMLv2 meetings. So what is different with SysMLv2 with respect to SysMLv1 is that it's not constrained by UML anymore. It has a new meta model that is grounded in formal semantics. It has an equivalent visual and or graphical and textual notation. And most importantly, it has a standardized API to access the model, right? Which kind of changes completely the picture, because now we can integrate it into this kind of pipeline, web-based web services pipeline. In this whole environment also, there's a lot of analysis and a lot of multiphysics simulations. FMI standard, FMI-FMU standard has become a key thing, kind of wrapping models and simulate them, co-simulate them, right, to enable like an end-to-end co-simulated representation of the system. One part that we see on the software side, in particular on Python, is there is a very Conda is used for all this package and dependency management for Python package, but we see that, or we would like to see that also for models, right? Now the models are kind of, send me the model, or you have some project usage or whatever mechanism. But I think what we would like to see is a more, actually might be able with SysMLv2, because there's also textual notation, to have like a Conda-based support for managing all those dependencies and distribution also, and reuse of those models, right? So like SysMLv2, FMI with Jupyter and Conda is kind of the package and dependency management piece. Which brings us to the next generation system engineers dream car, and where you have kind of Jupyter in the middle, Conda as package and package and dependency management, FMI, FMU, like as a wrapping, SysMLv2 as a core part for system level modeling, and OpenMB to bridge that gap between the documentation that we still have to produce and the models, the engineering models that we construct. And with that, thank you very much for your attention.
Thanks a lot, Robert. Yeah, very, very nice, very interesting talk. Yeah, giving this overview about how you working with JPL with all this pipeline, and and I would like to open to the audience. So, any questions from the audience? I'll check the chat here.
Who figured out why it's called Monsters and Dragons?
Yeah.
That's my question to the audience.
Come on. Okay. While people may be thinking about questions, I'd just like to a more general question. How, for instance, could you discuss a little bit about opportunities on how formal method strategy could? I know that there are some applications of formal methods already in this process. You showed that in the figure, but maybe discuss a little more about other opportunities for formal methods in this process as well. What do you think about it?
Yeah, I mean, I think it comes back to this paradigm shift, right, that I mentioned before. I mean, traditionally, particular system engineering is document natural language based, right? But what we see is also that more and more system engineers, in particular with Jupyter, right? It's so accessible, right, to people. I mean, you just use it, right? They don't have even to think much about it. And Python is permeating everything nowadays. So there's this shift to formal languages, right? And I think they are probably I think the formal methods come in, right? Because there was no way before to do anything with formal. I mean, it was more okay, like very like some spots, right, where it could be used. But with this shift to formal languages, but also to the automation part, which is a necessary step to kind of handle those systems, there is probably multiple entry points where formal methods could help. I mean, one thing that was there, and we have, we don't have it yet. We have just made experiments, right? But this like is the model checking part, right? For behavioral specifications. I think the big challenge is how do you handle scalability and with state space explosion and so on. I think in order to make formal methods more, let's say, kind of help supporting this kind of vision to move to formal languages, is the commodity, right? How accessible can it be in an environment to the average engineer, right? It will not help if an engineer has to learn about formal methods. No, that's not. Nobody will do that, or only maybe very, very, very few. So it has to be somehow behind the scenes, and it has to be scalable, right? I mean, it doesn't. So one has to probably constrain, or scalable or constrained, right? There are certain things that you can do, and we know these limitations, right? So I think it's this combination of, okay, how do we apply formal methods, whatever that might be, in a scalable or scoped, automated, accessible fashion. I think this is the thing one has to think about.
Yeah, indeed. And another more specific question related to digital twins. So because I'm entering in this area right now as well, and I was wondering the level of communications, for instance, of your digital twin with the real system. Do you have, because there is this concepts of digital shadow, digital twin, and so on.
Yeah, there's
and
a lot of buzzwords.
Yeah.
And very different interpretations.
Yeah, I was wondering if there is the possibility of the real system also provide feedback to update, for instance, your model or your digital twin.
I think that's something I've seen as well. I mean, I think most people, what I've seen is they think very much of the digital twin in terms of the as-built system, right? So you have some plant, for example, that is there, right? And you have to operate it, and it has sensors and actuators, and you get all those measurements, right, that you can analyze it. And then you have on the back end, or your back office, let's say, the digital twin of that operational environment, that can consume that data and kind of point out, okay, you have actually something is not going well there as expected. You might have to do some preventive maintenance before it breaks down, right? I think this is more like where currently I think the emphasis is. But I think we want to shift that from the operational part for sure is important, right? But I think we want to expand that to the very early phase, from early concept development on, right? So there might be in the beginning, if I just have a simple model with an executable state machine, that's already a digital twin, right?
Okay.
So that I think, and then when I do the model checking, generate the code, have parts of the code executed, those are, and then maybe have like a platform. So we have, like, when we test the software, right, there is some platform where that emulates like the spacecraft. It's not the real spacecraft. The software can run in an environment that makes it think it's running on the spacecraft, right? That's also a digital twin before even the spacecraft is there, right? And then in the end, even some hybrid environment, right, where the control software runs with parts of the real system, parts are simulated, right? So there's this whole spectrum of early on digital twin to the fully fledged one where you actually operate something, right? And I think this is also this idea of the Dragon architecture and the digital evolving fractal approach of the digital twin pipelines, right? You start very simple, increase fidelity, actually you have the real thing, right? So this is the vision that we have to kind of have this evolving digital twin pipelines from a very simple thing in the beginning to a digital twin of an operating system, operating environment, right? And ideally the scenarios that we kind of develop early on, we can use, or we should be able to use later on also for operations, right? There's no, if there's a disconnect, right? If you start very early on with some operation procedures, simple ones, right? But then in the end, you do something completely different, then you have again this disconnect, right? Instead, it should evolve, and we should be able, for example, to use this multi-physics representation of the system in order also to kind of, in our case, right, to navigate, for example, the rover on Mars, right? That's the idea.
Great. Yeah, okay. Somebody, questions?
They're all intimidated. Well, I'm friendly.
Yes, I actually know that.
Normal.
So I wanted to ask about this this kind of fractal approach and the fidelity that you keep mentioning. How is this related to refinement?
The what? Sorry, the audio cut off.
The increase in fidelity.
Yes.
But you say that early scenarios should be used.
Yes, yes.
So this seems to be quite strong. It seems like you imply that the whole development process is in fact refinement in the formal sense. So everything that you implement later should fit in anything that you said in the beginning.
Like it's like an envelope, right? And
yes.
we are more, so we define some envelope. Sorry, I interrupted. Finish
my question is, according to your experience, is this realistic? Because you also mentioned the change packages, and sometimes we just realize with maybe with formal methods or testing or simulation that this is not going to work, and we change our mind. And I figure that this should be documented, like these are design decisions or dead ends. But this feels like it contradicts with this continuous refinement.
No, so we worked recently on something with generative architectures, if that term resonates with you. So it kind of, you define your system model, right? You have defined multiplicities. For example, you have a number of batteries that you might use, or different number of wheels, like 4 or 6 or 8 or whatever, right? And you define kind of a system in like this. You articulate your design space, basically, right? And then you would use some generative architecture exploration environment to generate like a number of architectures, which nowadays we cannot do. I mean, there's like, most of the time we do some point designs, right? With like 1 or 2. And the trade space that we have actually closes very early, right? And we have to commit to hardware early. We want to expand that, right? So the generative architecture approach combines, so you would have maybe structure, which is the simplest approach, right? You define your components, your interfaces, and the variation points and so on, and then generate a number of architectures that you trade, right? But more importantly, include also behavior into that, right? Structure is simple, let's say, but as soon as behavior becomes more complex, right? So, and then there's this, and that will be like the functional level, let's say. One level, right? You have your architectures with different number of components, but then what we did is we actually project that into a multi-physics model with Modelica, right? So we have that let's say we pick one design, we project it into a multi-physics environment with Modelica and run there the simulations in that multi-physics environment, right? And can iterate there as well, right? And then there's this whole iteration, right? You kind of make changes, like you change the wheel size, the material, the battery size, whatever, right? So you can explore a lot more options. And with respect to the fidelity, right? In the beginning, you might have a very simple model, for example, of your battery, right? Or whatever component you have in your system, right? But as you kind of narrow down your trade space, right, with a few options, then you would increase the fidelity of those pieces, because you want to know more about good options in your architecture space. But those models, they should kind of in this Dragon architecture, right? They would kind of slide through and increase towards the end. You would, for example, when you have the software at some point, you would use those multi-physics models that you developed early on also to validate the software, right? So this is kind of the vision that we have, and partially we have done some prototypes. Let me show that one with the projection, but that's an interesting, very interesting, and actually works, and it's everything in Jupyter integrated, which is even more fabulous. So we can do all those projections and trades within the Jupyter environment, which is in Python, which is accessible, right, to many people. So that's somehow the way we're going. I mean, there will be dead ends for sure, and scalability issues, but I hope we can work them out.
Great. Yeah, I think we reach the limit, and if you have any question, sorry,
we should try to guess the dragon and monster analogy. Anybody?
Yeah, exactly. Who found out? No, that the original. I think the background is that before mathematicians, they knew about they didn't know about they called them monsters before they found out like the mathematical, because they could not explain it, right? So the fractal, the math behind the fractal. So they were originally called monsters until Mandelbrot, I think, found out the math behind it, and then that was the dragon, was one of the first computed structures. So we have the monsters that we don't know about, but then we use math as usual to kind of tame the monsters.
Yeah. My guess would have been that monsters, all these silos, are intimidating, while dragons are cool.
Okay.
Yeah, I have to find the right dragons.
That's right.
Yeah. So if you have any more questions, you can ask that in the Discord, and I can try to relay them to Robert later. And I was already asked Robert about the slides. He's going to send me, and we're going to post the slides on the website of the conference. Okay. So thank you very much, Robert, for your availability and this great talk for us in the conference. And we also looking forward to the next session, right? That we're going to delve into this pipeline, I believe, that you've shown here. So at least some of it. And yeah, for the time that we have. And yeah, in half an hour, I hope to meet you there and discuss how we can actually run and execute some of these things that Robert just gave us a glimpse here. Okay.
Okay, bye. Thanks a lot.
Bye-bye. See you.
Thank you. Bye.